Hello everyone. Today I'll be telling you about our work on protecting formally verified cryptographic libraries from Spectre style attacks. And this is joint work with the many wonderful co-authors listed here. It's well known that cryptography is really difficult to get right. Widely used libraries are constantly suffering from cryptographic design flaws, implementation bugs, and side channel vulnerabilities. And because they have such a large attack surface for security, crypto implementation should achieve what we call the Big Four guarantees. And so, implementation should be memory safe to prevent leaking secrets held in memory. They should be functionally correct with respect to some standard specification. They should be provably secure to rule out important classes of attacks. And finally, they should be constant time to avoid leaking secrets through timing side channels. And achieving any one of these is pretty difficult, let alone achieving all of them all at once. So to help, a lot of recent research looks to using high assurance cryptography techniques to develop high performance crypto code with formal machine checkable guarantees for the Big Four. But the bad news is that the Big Four guarantees can be undermined by recent microarchitectural side channel attacks such as Spectre, which exploit speculative execution in modern CPUs. In particular, Spectre-style attacks reveal a gap between formal guarantees of constant time, which hold for a sequential model of execution, and practice, where execution can be speculative and out of order. So this mismatch can cast doubts on the robustness of high assurance cryptography guarantees. So what we do in this work is that we set out to study the impact of speculative execution on high assurance crypto. And our main goal in this work is to extend the Big Four guarantees to a setting with speculative execution. Based on existing work by Sanjay, one of our co-authors, and others, we first formalize an adversarial program semantics for speculative execution. Then from this, we extend the classical notion of constant time, which works for a sequential setting, to the notion of speculative constant time, which works for a speculative setting. And one of our important contributions here is proving a key property, which we call secure forward consistency, which simplifies the verification of speculative constant time, and also proves that code proven correct and secure in a sequential semantics also enjoys these properties in a speculative semantics. Then, leveraging forward secure consistency, we develop a relatively standard two-step verification method for speculative constant time. So first, we check that programs don't perform illegal memory accesses, even under our speculative semantics. And then second, we check that program leakage doesn't depend on secrets. Third, we also integrate this verification method into the Jasmine verification framework. So previously, Jasmine could be used to develop high-speed cryptographic assembly code that enjoys the Big Four in a sequential setting, but now we've extended this to the speculative setting as well. And then finally, we use our extensions to the Jasmine framework to develop Spectre-protected implementations of the Cha-Cha-20 and Poly 1305 crypto schemes, and we benchmark their performance. Before we dive into things, let's first explain what the traditional notion of constant time is, how it protects against timing side channels, and what changes when speculative execution comes in the picture. For crypto code, even if it's functionally correct, it can still leak secrets through timing side channels if it executes for an observably different time depending on the value of secret information. For example, in the left code snippet, branching on a secret value can lead to a measurable timing variation since the body of the conditional is only executed if the secret value is true. The right code snippet is a bit more subtle. The first line loads a byte B from the secret array, and the second line loads a value from the table array using B. And in the second line, this secret dependent memory access leaks secret data since the lookup table of B will be brought into the cache. Then an attacker can infer the value of B by measuring timing variations when accessing different indices of the table array. So to protect against these timing side channels, the constant time programming policy disallows control flow and memory accesses that depend on secret values. It turns out that applying constant time coding recipes to turn secret dependent code into secret independent code is pretty unnatural and tricky to do correctly, so there are many existing tools that let developers annotate program inputs as either public or secret, and then automatically check that the program is constant time or else produce a violation. It is worth pointing out, though, that essentially all of these tools consider only a sequential model of execution in which instructions execute in order one after another. But we know that for modern CPUs, this isn't the case. They execute instructions out of order and speculatively to increase performance. For example, upon reaching a conditional branch, modern CPUs can use a branch predictor, known as the pattern history table, or PHT, to speculatively execute one of the branches before even resolving the branch condition. And so if the predicted path is correct, then the CPU commits speculatively computed results to the architectural state, giving us a performance boost. But otherwise, if the predicted branch is incorrect, then the CPU backtracks to the last correct state by discarding all speculatively computed results, and this gives us performance similar to idling, so we haven't lost much. And although the results of misspeculation aren't ever committed to the architectural state, remnants can still be left in the microarchitectural state, such as in the cache, which is the root cause of many recent high-profile Spectre attacks. To make things concrete, let's look at this code snippet, which is secure in a sequential world, but is vulnerable to what's called a Spectre PHT attack. The first line is a bounds check on X, which prevents reading secret memory outside of array 1, but unfortunately, an attacker can supply an out-of-bounds value for X, such that array 1 of X reads secret memory outside of array 1, and mistrain the PHT to speculatively bypass the bounds check, so that a secret value is stored in the variable I. Then in the third line, this loads the secret-dependent memory location array 2 of I into the cache, leading to a timing vulnerability. And memory fences can, in theory, protect against these vulnerabilities by acting as speculation barriers and preventing further speculation until prior instructions have completed. So for example, placing a fence instruction after the conditional branch prevents the CPU from speculatively reading from array 1 until the branch condition has been resolved. And at this point, any speculation will have been caught. But unfortunately, inserting fences after every conditional and before each load instruction, which is to protect against a different variant of Spectre called Spectre STL, which I don't have the time to cover, but is discussed in the paper, this really hurts performance. But on the other hand, taking a heuristic approach for inserting fences leads to shaky security guarantees. And so our solution is to automatically verify that implementations use fences correctly and efficiently to protect against Spectre-style attacks, specifically the Spectre PHT and Spectre STL variants. So now I'll explain some of the features of our adversarial semantics for speculative execution. For the sake of time, this will have to be pretty high level, but details can certainly be found in the paper. So we consider a core fragment of the Jasmine language with instructions for assignments, memory loads, memory stores, conditionals, loops, and fence instructions. States are stacks of configurations, which are 4 tuples of the following. Command C are sequences of instructions. Register maps row are maps from registers to values. Buffer memories mu consist of a main memory and a special write buffer, which contains a sequence of delayed memory writes. And this write buffer essentially models out-of-order execution on behalf of the CPU's memory disambiguator, which can be exploited to perform Spectre STL vulnerabilities. Again, see the paper for more details on that. And then finally, the Boolean B represents a misspeculation flag, which is set to true if misspeculation has previously occurred during execution and false otherwise. Our semantics is adversarial in the sense that program execution depends on directives issued by the adversary. So for example, at control flow points, the step directive allows execution to proceed normally, while the force B directive forces execution to follow the branch B. Our semantics is also instrumented with observations to model timing side-channel leakage. For example, the circle represents steps that don't leak observations. The adversary can observe the targets of memory accesses via read and write observations, and control flow via branch observations. And finally, the one-step execution relation is as follows, which is read as under directive D, the state S steps to state S prime with leakage O. So from our adversarial semantics, we define the following two notions. So first is speculative safety. So a program is speculatively safe if for every choice of directives, there are no illegal memory accesses. And our second notion is speculative constant time. And so a program is speculatively constant time if for every choice of directives, leaked observations don't depend on secret values. And armed with these two notions, now we can look at our previous example. So to see why this example from before isn't speculatively safe with respect to our semantics, we can take any initial state where x is out of bounds for indexing the array 1, and so the adversary is free to choose a directive schedule that forces the conditional to be true, and this leads to an illegal memory access to array 1 of x. And the argument for why this example isn't speculatively constant time is a bit more subtle. At a high level, in our semantics, unsafe accesses conservatively leak the entire program memory via an unsafe observation, and so leaked observations do depend on secret values, thereby violating speculative constant time. We additionally develop a weaker forward semantics in which executions are forced into early termination when misspeculations is detected. And from this, we prove a key property of our semantics called secure forward consistency, which says that a program is speculatively constant time if and only if forward executions don't leak secrets. And this key property has two main benefits. First, it greatly simplifies the verification of speculative constant time because we now have to consider less execution paths. And also, it says that correctness and provable security carry over from the sequential semantics to the speculative semantics. And so based on these results, we develop and integrate new verification methods into the Jasmine framework and perform two case studies for Cha-Cha-20 and Poly 1305. So we developed verified implementations, both a scalar version and an optimized version that uses AVX2 instructions, and these implementations enjoy correctness, speculative safety, and speculatively constant time. And our case study showed that most of the development effort was in fixing speculative safety issues. After that, there was relatively additional work to achieve speculative constant time. And moreover, functional equivalence proofs with implementations proven correct in a sequential setting were mostly automatic. We also evaluated the performance overhead of our Spectre protected implementations. Here we'll just look at Cha-Cha-20. And so these plots show the cycles per byte for processing messages of varying length, where lower is better. So on the left is the scalar implementations. The purple line is the unverified OpenSSL implementation. The blue line is the non-Spectre protected Jasmine implementation. And the green line is the Spectre protected Jasmine implementation. So as we can see, Spectre protections only come with a modest performance overhead. And for the AVX2 implementations on the right, this shows that Spectre protections come with almost for free performance-wise. And so to conclude, the key findings of our work are that algorithms for proving speculative constant time aren't much harder than those for constant time. Existing approaches for the Big Four can be lifted to the speculative setting, and the performance overhead of making code speculatively constant time is relatively modest. So with that, I hope I piqued your interest in our work. If you're interested in learning more, I hope that you'll check out our paper, and I'll be happy to take any questions. Thanks.